we are going to do our second lecture from Chapter 7, where we are talking about entropy. And we're going to define it more as a property. We sort of launched into it yesterday of talking about what it was before we talked about how to work with it. So we're going to talk about how to work with it today. And we're going to divide up the types of problems for entropy into two different types of problems. One, we're going to start with talking about entropy for a closed system, and the other one we're going to start talking about entropy for an open system or a control volume. So we'll get started with that today. So let's turn over to the document camera, and we're going to discuss more about entropy. We're going to start to work with it in a engineering fashion. In other words, we know what it is, or what it indicates, what it means, and now we're going to talk about how to do it. So the first thing about entropy, we know that any real process, for any real process, entropy increases. And one of the ways that we deal with that is we can say, I think they just refer to it as S, not delta S. Yes. S generated is greater than or equal to 0 for a purely reversible reaction, greater than 0 for a real reaction, less than 0 only for an impossible, even theoretically impossible reaction. All right, so if you look at entropy, we talk about it in a couple of different ways. But we've said that delta S of a system is equal to S2 at S at time 2 minus S at time 1. And this implies that it is a state property. It is a state property because we define entropy for what entropy would be, what the change in entropy would be for a reversible reaction, and then we compare a real reaction to it, which is where this S-generated term comes into it. So there S is associated with mass, heat transfer, let's say mass transfer, mass in and out of the system, heat transfer, the state within the control volume, but S is equal to 0 for work. So in other words, if you have that work term, if you have work, the entropy associated with that is equal to 0. All right. So when we talk about entropy, we only really are looking at it in terms of the state of the system and also the heat that goes in and out of the system. All right. So I'm going to write an equation up for you, and then we're going to talk about where the terms would come from when you're working your homework. All right. So I'm going to the chapter review. So looking at page 396. We're going to talk about entropy for a closed system, first of all. And the way that they write it here for a closed system is that the entropy that goes into the system minus the entropy that goes out of a system is equal to, they added over here, plus the entropy generated by the process is going to equal the change in entropy of the system. Now, in general, if we do not have mass going in and out, all of this entropy, we know that the only way that energy can enter or leave a system is by a heat transfer. And we further know that the integral of del Q over T is approximately equal to S in or S out. And if the temperature, this would be the temperature of the surroundings, okay? And this is the heat exchanged between the system and the surroundings. So if T0 is constant, in other words, if we are exchanging with a heat reservoir, either a source or a sink, where the heat exchange is small enough that the temperature of the reservoir doesn't change, that will come out of the integral, and we'll just get the integral of del Q over T, which is just equal to the Q over T term. So for a closed system, S in and S out are almost always any heat that goes into the system over T of the surroundings, which I'm just going to call T sub 0, minus Q that goes out of the system over T sub 0, plus S generated equals the change in entropy of the system, which is S at time 2 minus S at time 1. And so now the question is, where do all these terms come from? Well, first of all, generally speaking, you either have Q in or Q out. And how do you find that? We've been doing this for a while now. How do you find the heat that goes in or out of a system? What law of thermodynamics do you use? We've only used one, so which one do you think it is? Yes, by using the first law. Thank you, Jacques. So, since we only have one, the options for elimination are quite small. So basically we do this. Q minus W equals delta E of the system, which is delta U plus delta PE plus delta KE. So we're on firm ground here, aren't we? So in other words, if we just determine what Q is, we could just add the work to it over here, like that. And then we can determine if the heat goes in or out of the system. Then we decide if it goes here or here, and we divide it by the temperature. And that's how we find Q over T sub 0. So in other words, the only thing that we need to know that we didn't necessarily need to know before is the temperature of our surroundings. S2 and S1 are state properties, and they are in our tables, which I'm going to show you in just a moment. And S generated is always a calculated term. Once in a while, they'll give it to you, but they had to calculate it. So in other words, you don't find it from a table. It's from process of elimination. It's what's left over when we know Q over T and S2 and S1, right? And the process of doing this is just slightly more complicated when we have an open system, just like it's slightly more complicated to do a first law analysis and a material balance or a mass balance analysis when we have an open system. But for a closed system, this is what it amounts to. All right, so now let's talk about S2 and S1. State properties, they're found in the property tables. So let's swing over here to the computer and look at our property tables, which are up on the Moodle page. Okay. So here in our course, thermodynamics, get rid of that. Good for him for having that up there, but here we go. Thermodynamic property tables. So let's just look at the SI units to begin with. When we come down here to water, for example, here's my saturated water table based on temperature. You see that we have temperature and pressure. That's saturation conditions. That's what keeps us in the two-phase region. Our first two columns are V sub F and V sub G, specific volume. Our next three columns are U sub F, U sub FG, and U sub G. So in other words, those are our internal energy. Next three columns are our enthalpy. And look over here. What's over here? Entropy. That is exactly correct. And you'll notice that it's given the designation, little s, so we have little s sub f, that is the entropy of the left-hand side of the two-phase envelope, S sub fg, which is the arithmetic difference between S sub g and S sub f, and S sub g, which is on the right-hand side of the table. Now, one thing I want to point out, too, is the value here at a temperature for water of 0.01 degree and a saturation pressure of 0.6 kPa, which is very, very low, of course. That is defined, S sub f at that point is defined as being 0. If you've noticed, we've always talked about delta S's. We've not really talked about absolute values of S's because absolute values of S's are compared actually to absolute 0. So what they've done in the tables, and this happens in all S tables, all tables that tabulate entropy, you're always going to be looking for a difference. You're always going to be looking for S sub 2 minus S sub 1 in some way. So these are all based on some arbitrary condition. And water at 0 degrees centigrade in the liquid phase is a common reference point. So that would be 0. But they can use different reference points as all. All that means for you is you don't ever want to bounce between two tables when you're getting a delta S. It's possible that they could use a different reference frame. Okay? So you always want to use one set of tables. Now, that also means that an S could be negative because it's a difference. So if you were below this condition, if you had a compressed liquid water or ice, the S value may be less than 0. You just have to use it by S sub 2 minus S sub 1, and you'll be fine. All right? So it's not really S, it's really a delta S, where the delta is always the same base. Right? So anyway, those are your values. You also notice the units, kilojoules per kilogram degree Kelvin. Well, that is consistent with this term. If you look at Q over T, capital Q would be kilojoules, but little q would be kilojoules per kilogram. And when you divide by temperature, it's by degree Kelvin. So little s is always kilojoules per kilogram degree Kelvin in the SI system. Capital Q would be just kilojoules per degree Kelvin. Those are the correct units. And so they're reflected in both this equation and the units of entropy, right? So this is the way that it works when we are talking about doing a second law balance on a closed system. It always looks like this. This is the term you're always looking for. The question is always, will this process work or not? And the answer to that is whether S generated is negative or positive. If S generated is positive, yes, it will work. If S generated is 0, it will not work because it's a reversible equation. If S gen is less than 0, it will not work because it's an impossible problem. Okay? So before we take a look at a problem in the textbook, I want to refer back to the example that I really love. And when you pull this together, you'll see that there's a lot in this that will help you to work out problems. But the water to steam or steam to water. The reason I love this problem is because it's something that we already know what's going to happen. So if you look at the signs of everything, you can determine what signs look like when you're working a problem. So if you ever, because the confusing part really is whether Q is positive or Q is negative in the problem. And this will illuminate that for you. Okay? So once again, you look at this, how do you work with this? Steam to water, water to steam, which will happen? That's always what the second law answers. Will this process occur, or which way will it occur? Okay? So here we have steam to water. I've set the conditions. I've given you the conditions of the steam, the pressure and the temperature, plus this new piece of information that, like I said, we have to have now is the ambient temp. Yeah?
Is S of steam always going to be S2?
Oh, good question. No, only if steam is the final state. Okay. So S2 is the final state. Great question. So actually that's what happens in this problem is the value of S2 and S1 reverse, and that changes the sign of the Q. See, I told you there's so much that you can get out of this problem. All right, so we do the way that, once again, you always work a closed system, and I'm pretending that this steam is in a magic force field bubble, right? It's not evaporating into the room, it's just, it's being contained in some way so that we're capturing all the steam. It's a closed system. All right, so first law, Q minus W equals delta U, because there's no change in PE or KE. Bring work over to the other side. Since it's isobaric, it's P delta V, so just by a trick, delta U plus P delta V is equal to delta H. Little q is equal to little delta H. So I picked up H2 and H1, my enthalpy values, out of the table, and I calculate Q. H2 here, because we are talking about steam going into water. Water has a lower enthalpy value than does steam, so my Q is negative. That means that for steam to condense to water, heat goes out of the system. So my Q out, there's two ways to look at this. Don't do both. This is where you get into problems with the sign convention. Q is negative 2256.5 kilojoules per kilogram, which means that Q out is 2256.5 kilojoules per kilogram. Okay? So then the next thing we ask is, will this occur? S in minus S out plus S generated equals delta S system. That's just the equation from page 396 of your textbook, rewritten on our notes and rewritten here. There's no S in, right, because all of our heat's going out, is what I'm telling you. So we're going to solve for S generated, which is equal to delta S of the system plus S out, because this is negative over here on the left. You bring it over to the right. Arithmetically, it adds. So we have the value of Q out, which is 2256.5. It's not negative, is it? Q out is what I'm talking about. Q out is 2256.5. Okay?
How's Q in negative and Q out?
There is no Q in. Right. So what I'm saying is the way this equation is written, it's S in minus S out. So when you calculate S out, it's based on Q out, which is a positive. Now, I'm going to say something really confusing. I'm not going to write this down. You could look at S in and say, well, S in is negative because it went out, and then you could put S in as being a negative value. You don't want to do that. Just think about whether it's going in or out. That's it, okay? So anyway, so then we calculate S generated. S generated here is positive, so that means it will occur. All right, now let's do it the opposite way. If we go liquid to steam, here we answer Jess's first question. Our H2 in this case is H of steam. H1 is H of water. So this time, my heat is 2256. That means Q has to go in to make this work, right? The first law doesn't tell me if Q will go in or not, but we know that it will. So here we have S in is positive. S out is nothing because Q goes in. That means when we bring S in, which is positive on the right-hand side, it becomes negative on, positive on the left-hand side, it becomes positive on the right-hand side. And we solve for S generated, which turns out in this case to be a negative number. Negative S generated means no bueno, it does not happen. Okay? So do you see how that works? Now the other question is, and this is a little bit more sophisticated, but what would cause this to occur? Well, let's think about it. If you have water turning into steam, how do you have to have that happen? You're going to have a really hot room, right? It's going to have to be above the boiling temperature of steam. So you can actually use that idea to find out what temperature you would need. And once again, I like this because you already kind of know what that is. It's about 100 degrees centigrade, isn't it? You'd have to maintain 100 degrees centigrade. So if now you say, well, let's call S generated equal to 0, or just a little tiny bit above 0, because we need to generate just a hair of entropy by this process. What does our temperature have to be? Turns out 106 degrees centigrade. And that makes sense, doesn't it? In other words, we have to be slightly above the boiling temperature of water in order for the water to boil. Right? It's like, we already knew that. But it's like, we already knew that. But now we know it mathematically, and we can do it for processes that we don't know which way they're going to go. Jess, do you have a question? Not yet. Yes. Okay, I understand.
Just trying to
wrap your head around it?
Digest.
Yes, digest. All right. Well, what we'll do is we will work a single problem from your textbook, and then I have not posted homework for chapter 7 yet, but I will post it. So start working through it, and that's how we learn, right? That's the key. So we'll do a problem, and then we'll call it a day. Okay, let's look at problem 741. Right. 741 says a rigid tank. Rigid means that is code for the volume does not change, right? Okay. A rigid tank contains 5 kilograms of saturated vapor steam at 100 degrees centigrade. Saturated means, saturated steam means we are X is equal to 1, right? In other words, we are on this side of the curve right here. That's our state 1. The steam is cooled to the ambient temperature. That means Q goes out. And so this is state 1. I better not say S1 because that looks like entropy, doesn't, or enthalpy. Entropy, sorry. And this is state 2. So we still have 5 kilograms. The volume here is the same as the volume before. That means that the specific volume here is the same as the specific volume before. We don't know where we are. We don't know if it's compressed liquid water. We don't know if it's still in the 2-phase region. We don't know anything about it. But we know that the temperature here is 25 degrees centigrade. And we know that T sub 0 is 25 degrees centigrade. All right? It asks us to sketch this process with respect to saturation lines. We already kind of started it. And then it asks us to determine the entropy change of the steam. That's S2 minus S1. And last, for the steam and its surrounding, determine the total entropy change associated with the process, which is really asking for the S generated by this process. Okay? So let's take a look. Well, the first thing we have to do is to define the states, just like we always have. We have to write out the first law of thermodynamics. Q minus W equals delta U plus delta PE plus delta KE. It's a rigid tank. That means that the integral of PdV is equal to 0, so work is equal to 0. There is no particular change in potential or kinetic energy. So the first law just reduces to the idea that Q is equal to delta U. All right, so we can define this state because we know we're at 100 degrees and we are at X is equal to 1. We can find U at state 1 is equal to U sub G at that condition. We can also find that S at that condition is equal to S sub G. Okay, and we're going to have to fix the condition here. Let's just take a look at specific volume, because one thing that you can see is that the specific volume here is equal to V sub G. But the other thing is because the mass and the volume here are the same, the specific volume over here at time 2 has to be equal to the specific volume at time 1. Because the volume is the same and the mass is the same. We can use that idea to fix our state 2, can't we? Okay? Because we have a temperature, we know it's steam, and if we have V sub 2, we'll be able to fix it. All right, so let's go back to our temperature tables, or excuse me, our steam tables. In the first case, we're at 100 degrees, and we're saturated water. So this is the conditions that we're looking at right here. Okay, so I know it doesn't really matter, but I'm going to write it down that my pressure is my pressure of saturation, which is 101.42 kPa. We can pick up these values. My U is my U sub G value, which is 2506. My S is equal to my S sub G, which is 7.3542. And the units are all metric units or SI units. I'm not going to pick them up right now. V sub 1, which is what I'm going to use to fix my state, is 1.672. All right. All right, now here's the deal. When we write this down and we look at what we have going on, we know that my specific volume is going to remain unchanged. So my specific volume over here is 1.672. And those units, I'm going to write them over here. I didn't really have room over here, but cubic meters per kilogram. And my temperature is 25 degrees centigrade. Now, if I go up here in my, I'm trying to fix my state on state 2. If I look at 25 degrees centigrade, and I look at my V values, look what I have. My V is in between this and this, isn't it? Okay, so that means, oddly enough, even though we lost heat, we now are, well, I guess it's not odd, but we're in the two-phase region, but we're not at 0 or at x equals 0 or x equals 1. We're somewhere in between. So let's find our x value before we get started. The other piece of information is that we can find our u after we find x. So let's find our u sub f and our u sub g. And then we're going to need to do the same with our entropy. So let's pick up these values out of the table so that we can use them after we use v to find our x. All right. So u sub f is 104.83. U sub g is 2409. Am I on the right screen? Yep, 2409.1. S sub f is 0.3672. And S sub g is 8.5567. All right. So let's go back and use our v value to compute our x. Well, we know that for any value v, for any x value, v is going to be v sub f plus x times v sub g minus v sub f. And if I rearrange this, I can solve for my x value. So that's the first thing that I want to do. So I take my v, 1.672, subtract from that the v sub f. Did I not write those down? Well, that was silly. Let me write down my v values. V sub g is 43.34. And my v sub f value is 0.001003. And when I do the two subtractions and the division, I will get my x value. Now I'm going to approximate it. If you look at that v sub f value, it's tiny. So I'm going to just eliminate it from the calculation. I'm going to be a little off if you redo this, but I'm just going to take 1.672 and divide it by 43.34, just for the sake of time. So I get an x value of approximately 0.0386, 0.0386. So what that means is, if you recall, 1 is here, x of 1 is here, x of 0 is here. So we are almost all steam, aren't we? We are just right here. So the first thing is, this is what our sketch looks like. We start here, we end up here. We're almost over to all liquid. Or excuse me. Yeah, that's right. Yep, 0. Sorry, I just had a minute. Never mind. But we're good. All right, so now let's find our Q. We know our U sub 1 value. We need to find our U sub 2 value. We do that using our x. We know that the u, going back to this formula again, the same thing, any property, is going to equal u sub f plus x times u sub g minus u sub f. So right here, u sub 2 is equal to 104.83 plus x, which is 0.0386 times u sub g, 2409.1 minus 104.83. Okay. And I do the math on that one. 2409.1. Subtract from that my u sub f value, 104.83. Multiply it by x, 0.0386. And that's 88 plus some stuff. Add to that 104.83. And I get 193. So my u sub 2 value is 193.77. And that's going to be in kilojoules per kilogram. So my Q is going to be delta U, U2 minus U1, which is mass times little u2 minus little u1. So Q is equal to 5 kilos times the quantity 193.77 minus my u1, 2506. Yep, and 0.0. It's okay, so I take this number, 193.77, and subtract 2506. That's a negative number. Multiply it by 5. And that is, Q then is 11561. This would be in kilojoules per kilogram. Multiplied by kilogram gives me kilojoules. And the value is negative. Okay? So what that means is Q out is 11,561 kilojoules in this problem. All right. The next thing I want to know, this is going to come in handy for part 3. We don't really need it for part 2, but we'll work on part B next. B says, what is the change in entropy S2 minus S1? That's going to be equal mass times little s2 minus little s1. S2, because it's a state property, I find it exactly the same way. S2 is going to be S sub F plus X times the quantity S sub G minus S sub F. So here is 0.3672 plus my X value, 0.0386 times S sub G, 8.5567, minus S sub F, 0.3672. And those units are going to be kilojoules per kilogram degree Kelvin. Okay, so here's my cursor. Let's go ahead and do the math. 8.5567 minus 0.3672. Multiply that by my X, 0.0386. Oh, my calculator just went away. That was fun. Let's do it again. All right. And add to that number 0.3672. So my entropy at the second state, S2, is 0.6833147 kilojoules per kilogram Kelvin. So that means that if I take my mass of 5 kilograms, multiply it by 6832 minus S1, which is S sub G, 7.3542. I get, can you see where I'm working? Right here, yes. So I've got this number, 0.68, whatever, minus 7.3542. And I multiply that number by 5 kilograms, and I get a value. My S2 minus S1 then is equal to negative 33.35, and I've multiplied by kilograms, so that's kilojoules per degree Kelvin. So I've actually lost entropy in the process. So the only chance I have of having this be a real reaction is if the heat going out generated enough entropy to actually make it occur, right? So let's find out. So going back to this equation, we're going to find S generated. And I go back to the original equation that I used from page 396 of your textbook that says S in minus S out plus S generated equals delta S of the system. Okay, well, our heat goes out, so there's none of this. And I can say S generated, this comes over as a positive, equals delta S of the system plus S out. And S out is the integral of Q over T, which is just Q over T because, the integral of Q dQ over T. So this is just Q out over T because we're assuming that that temperature stays constant, plus the delta S of the system. So from my calculation, delta S of the system is negative 33.35 kilojoules per kilogram. My Q out is 11,561 kilojoules over my temperature. I'm told that the ambient temperature is 25 degrees centigrade. I need to convert it into kelvins, so I add 273. And let's see what happens. Let's find out this quantity first of all. If I take 25 and add 273, I get that my temperature in Kelvin is 293. And if I take the reciprocal of that and multiply it by 11561, I get 38.79. So do you see how that's going to become a positive number? Because this has a higher absolute value than this. So my positive value from the heat transfer of entropy is greater than the absolute value of this. So what I end up with is a positive value here, minus 33.37, and I get 5.42. So my S generated in this process is 5.42 kilojoules per degree Kelvin. Therefore, the process will work. Process will occur. I guess may occur would be a better idea. In other words, it is not violated by the second law of thermodynamics. Or it doesn't violate the second law of thermodynamics would be a better way to put it. So do you guys have any questions about that? All right. So I'll post this lecture. I will post the homework problems. And all of that will be done by the end of the day tomorrow. So I would like to get it done today, but we'll see what happens. So by the end of the day tomorrow, everything will be posted. And next Tuesday, no class because it's advising day. Now, for anybody who's watching this on video, if it's not 2018, that is not true. This is for this is for this day in 2018. I apologize for making that timestamp. Anyway, so we will continue with our discussion in our next vlog, at which time we will finish chapter 7. So you guys have a great day.